welcome to the hello.
Yeah, you're live. You're live. Let's do it. Let's go.
Hello, and welcome to a brand new episode of Quirkcast. I'm your host, Mikey.
And this is your host, Sahil. Welcome, everybody, to a brand new, exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern. Do ask us questions during the episode, and we'll get to it. So, without further ado, let's get to it. So we have a little bit of a technical situation that's a little bit tricky, where our video isn't necessarily working. So it's just going to be a webcam on me, but Mikey's on the phone. Please message in the chat if you can't hear Mikey. But yeah, we'll try to do our best, and if it doesn't work, we'll see what we can do. So Mikey, we were talking about doing an episode on spin. But before we get to that, it was we were trying to discuss like how to how to really describe spin. So I think we should start with the concept of angular momentum. Like, what is angular momentum to start out with?
Yeah, definitely. Yeah, I mean, spin is just a really, really weird thing. It's completely not intuitive. I guess the only thing that it has even a remote connection to in our everyday world is this concept you just mentioned called angular momentum. And I guess angular momentum is pretty obscure to a lot of people as well. But I think the way I would describe angular momentum, so I guess we could back up even further and talk about momentum, right?
Yeah.
So in our universe, there are a few kind of like sacred quantities, I would say. I think most people have probably heard of like conservation of energy. Energy cannot be created or destroyed. It can only change form. So energy is an example of like one of these like quote unquote sacred quantities that is really important in our universe, and our universe respects this quantity and it doesn't change it. Another one is momentum. So for those of you that have studied like Newton's laws, one of them says that objects in motion will stay in motion with a constant velocity unless acted on by a force. And that's because of conservation of momentum. Once you have some momentum, the universe really, really tries hard to make sure that you maintain that same momentum unless some force stops you or something like that. So energy is conserved, momentum is conserved, and I guess now coming to angular momentum is like rotational, like the rotational analog of momentum. And it's a little weird, but if you think about like the reason why bicycles work, the wheels are spinning around a certain axis, and the universe wants that spinning to maintain itself around the same axis. And that's why when you ride a bike, you don't fall over. The wheels are spinning fast enough. I don't know. Sometimes like at science fairs, they have that thing where you can actually hold a spinning bike wheel and try to turn it, and you can feel the universe trying to resist your attempt to change the direction of motion of the spinning wheel.
Oh, fascinating. Interesting. I guess what was the need to like, why can't you explain that with momentum instead? Why do we need angular momentum?
Because with momentum, with linear momentum, there's no idea of like an axis of rotation. So momentum is conserved. Linear momentum is conserved. That means that objects in motion stay in motion. But rotational objects, they try to maintain the axis of rotation, and they will resist your attempt to try to change that axis of rotation.
Okay. So are there other places where this appears, like maybe in the cosmos or something, more than just bicycle wheels, angular momentum?
Every single spinning object like any kind of rotational motion. So like linear motion and rotational motion are two very special kinds of motion that the universe tries to like maintain, tries to keep constant. Yeah, so every galaxy, every solar system has, has a angular momentum that you can calculate, and yeah.
So when you say, just to clarify, when you say linear momentum, you're referring to just momentum, like movement in a straight line.
Yeah, straight line motion versus like spinning motion. Those are the two special types of motions.
Gotcha. So I guess like so when you like take classical physics, you learn about energy, momentum, and angular momentum. Now, we all know the world is quantum mechanical. So I guess, is there like a quantum mechanical analog? Is it just more of the same, or like what happens in quantum mechanics if we kind of dig deep into that?
Why would you think there would be a quantum mechanical analog?
I don't know. I have a bit of an intuition about it.
It's because no, it's completely crazy that there's a quantum mechanical analog, right?
Yeah.
Like,
yeah.
It doesn't. It's weird. Like, but it was I don't know. I forget exactly how spin was discovered, but I'm sure the full character of it was not appreciated for, I don't know, probably several decades. It's just a weird thing that like when you see particles, they have this behavior as if they're kind of spinning around on an axis. They have some angular momentum, even though, as far as we know, they're just single points. So they can't actually be spinning. There's other arguments for why you can actually prove that an electron, for example, is not actually spinning around like a top, but it somehow has this property as if it was spinning around like a top.
Interesting. So I guess, is that come to our I guess title of our episode about spin? Is that property called spin?
Yeah, and it's like it's named that way because of the the word spin has that intuition for us, like angular momentum. Anything that spins, anything that rotates has angular momentum. But it turns out that particles, which aren't spinning, still have this rotational property associated with them, and it's totally bizarre.
So wait, hold on a sec. I think I heard two maybe not contradicting, but two different things. Like, one is this analog of like, as if particles, it's its own top and it's spinning about itself. And then you're mentioning when it's not spinning, it's spinning. Or can you break that down further?
Yeah, I forget you can actually, there's a calculation that everyone has to do in grad school where you have to prove that an electron can't actually be spinning. I think, so when we look at like a point-like particle, it has this property where it seems to have like this axis of rotation that resists change and tries to be conserved. But there's a calculation you can do where I think, and you can actually measure the rate at which it's spinning. And I think the calculation is something like if you actually look at that rate and you look at kind of the extent of the electron, it would have to be spinning like faster than the speed of light or something, which violates the laws of physics. So it's not actually spinning, but it somehow has a spinny property, and it spins at a very particular rate.
I see. Before we get to how to conceptualize this, is this spin is it like continuous in the sense of, in like classical physics, the Earth could be rotating around the sun in with arbitrary precision type of angular momentum, or is it like discrete, or like how do we think about this?
It's really, really, really weird. It can rotate. The axis of rotation is arbitrary.
Yeah.
But oh gosh, now we're going to get into like the weirdness of quantum mechanics. But when you try to measure which axis it's rotating around, you will always either find it rotating along that axis or in the opposite direction. So quantum mechanics, like the observer affects the actual object. So if you try to measure it its axis of rotation, let's say on the x-axis.
Yeah.
If I imagine some XYZ coordinate system,
Mm-hmm.
You're always going to measure it either plus x or minus x. You're never actually going to measure it to be, like 45-degree angle between x and y or something.
Oh, how interesting. And I'm sure if you were to rotate your axes and like measure along that direction, then
exactly
you wouldn't be able to measure anything like orthogonal and whatnot, is what you're saying.
Yeah, exactly. Yeah.
I see.
So your measurement, in a sense, affects the direction in which it's spinning, but you can measure along any direction. So in that sense, the direction of the what is it? What was he calling it? The direction of
the x-axis, right?
The axis of rotation.
Axis of rotation.
In that sense, the axis of rotation is arbitrary, but it's determined by how you measure it.
I see. Okay, so
it's totally weird. It makes no sense. You just it's one of those things where it's just so foreign to human intuition where like as a physicist, when you learn it, you just have to like work it into your brain until it just becomes like normal. But there's no easy way to do it.
Yeah. Okay, so let me kind of take a step back and summarize, at least do my best to summarize what we've talked, because we've talked about a lot of different things, and I kind of want to glue it all together as best as I can. So in quantum mechanics, you have this quantum mechanical analog of angular momentum that we call spin. It's just a property of various different particles. In the case of like an electron, as we've been discussing, the spin can orient in like any one of the three directions, X, Y, Z, or some combination of them. But if you measure in a particular direction, it'll either be like, let's say X direction plus X minus X, but you won't know anything about the Y or Z direction. And if you try measuring Y or Z, you won't know anything about X. You'll lose information, or not lose information, but you'll have uncertainty about where it's spinning in X direction. And then also to clarify further, it's not actually, you can visualize it to help visualize it easier as if it's spinning about itself, but it's not really like a ball spinning. It's more complicated, or just no one really knows what that actually is. Is that fair?
In a weird way, it's not more complicated. It's more simple. It's like more simple than you would think would be possible. It's just an intrinsic property of this thing is a behavior that is analogous to a spinning object. But it's not because it's spinning, it's just an intrinsic property of it. It's like, it's more simple than what would make sense.
Yeah. So I guess one thing I want to ask, just to clarify, is how do we know that spin is angular momentum and not like momentum or maybe some other quantity? Like, what in experiments have we been able to see that it's like, is angular momentum like? Because if it's not actually spinning about itself, how can I take like this classical intuition and apply it to quantum mechanics?
So what's the best answer to that question? I'm not sure if the first answer that pops in my head is going to be the best answer.
May I suggest a possible experiment that you could talk about, possibly, that ties to
Oh yeah, well I guess the first one was like, when you take spinning objects that have a charge and you throw them in a magnetic field, that spinning motion, that rotation affects the actual linear path, like a spinning object will curve in a magnetic field. And that was actually, I think, how it was first observed. You shoot electrons through a magnetic field and you notice that they either go up or go down as if they were spinning either along the plus axis, x-axis, or the minus x-axis. So they literally, like because a lot of these particles that have spin, because they are also electrically charged, we can observe their behavior to be identical to that of like a rotating metal ball, for example.
That makes sense. And if I'm not, just for the aficionados out there, I think it's called the Stern-Gerlach experiment, if I'm not mistaken.
Yeah, that's right.
Yeah. So okay, so that makes sense as it being related to angular momentum. So I would kind of want to go more on the like application side in some sense in the remaining time that we have. Like, Yeah, so it has this intrinsic property. How do, scientists leverage this property of electrons? Like, what are in your mind, what are the really cool things that we can do with electrons having spin, or maybe particles like electrons having spin?
Wait, before we talk about that, can
Yeah.
we talk about just another just totally weird thing about this intrinsic spin property? Is every electron spins at exactly the same rate.
Oh.
And that rate is Planck's constant divided by 2.
Mm-hmm.
So, and when particles, so I guess you could say at the quantum level, the rate of rotation, the direction of rotation, as we discussed, can be arbitrary. Up to the fact that you control it by measurement, but the rate of rotation is absolutely not arbitrary. There's only a few specific allowed rates of rotation for particles, and it's either 1/2 of Planck's constant, 3/2, 2. They come in these discretized rates, and that's totally weird.
Yeah.
Yeah. So I don't know. It would be bad not to mention that. That's just like the weirdest thing about this spin property. Yeah, and I think, of course, like the coolest application of spin in particles is, we discussed how when you actually measure the axis of rotation along a certain direction, you always measure it to be either plus, either like in that direction or in the opposite direction. So it's kind of like a binary system, except it's more powerful than a binary system because it's not just like, ones and zeros. It's not just plus and minus. Yeah. But as we mentioned, you kind of have the freedom to measure it along any axis you want. So there is more information in there than just binary, but it has this binary property, which means you can digitize it and encode information in it, and that's really what quantum computers are all about.
Yeah. Oh, that is an interesting thing. So can we, I guess maybe, I mean, we could delve into quantum computing more in depth in probably another episode, or we've talked about it here and there in previous episodes, but at a high level, like, what is kind of the difference between, like, I guess a 0 and 1 versus like this, I don't know, they're called qubit, quantum bit, for example.
Yeah, the biggest difference is that, so like with a 1 and a 0, like with classical binary, there's exactly 2 pieces of information in it, or I guess 1 piece of information, like yes or no, right? It's like it's a single question, but because of this strange fact that the axis of rotation is arbitrary, there's a lot more information. Like an electron, when you measure the direction, the axis of rotation, it's like a yes or no answer, but there's more than, because you can ask, what's a good analogy?
Would an analogy kind of be like there's also certain, loosely speaking, probabilities associated with measuring it, like say in the x direction, plus x, minus x, and because the quantum state is storing, like, these probabilities, it's storing way more information, like a definitive, like 0 or 1, but it's like, in superposition. Is that a fair statement?
Yeah, but that's a little too advanced, I feel. Yeah, like, because you could kind of imagine a probabilistic classical binary system as well.
I see.
But yeah, but the quantum version is more than that, because it's not just yes or no, but okay, so like I guess with classical binary, it's like you can ask a yes or no question and you'll get yes or no, like binary, 2 possibilities. But with something like the electron, it's also yes and no, but because you can measure it along any kind of axis, it's like having yes or no answers to an infinite number of questions. instead of just one
Mm,
question.
I'll take it. There's actually pertaining to this, there's an audience question that asks, can these spins encode bits of information and transmit without actually transmitting?
Without actually, what does that mean?
I guess, like, you know, when you're operating a classical computer, electrons have to move through like a circuit, or I'm not exactly, you know, as familiar with the subject, but you have to send an electrical current to change like a 0 to 1 and a 1 to 0. But like in a quantum computer, like, do you have to also send like an electrical current to like change things around, or?
I think probably what the person is asking about is related to this idea of quantum teleportation, which, you know, has to do with the fact that, it's going to bring us slightly off topic, but another fact about quantum mechanical systems is that there's this property called entanglement, where two physically separated objects can have kind of a shared property. But I think it's important to note that even with quantum teleportation, there's no actual information being communicated faster than the speed of light. Like, the outcomes are already determined. So in a sense, it does require transmission, like some kind of physical transmission. And if you look at these quantum teleportation protocols, they always secretly involve actually moving an object from one place. It's not actual teleportation.
I see. Yeah. I see. That makes sense. I guess, like, so with I guess with quantum computing, that's another application of like of spin, for instance, leveraging, because if electrons didn't have any spin, let's say that property didn't exist, would you have quantum computing?
No, I don't think you'd have a universe. It's weird. It's weird. It's like we invented computers, and we have this kind of like lame version of like binary that we use to encode things, and the universe has a much more sophisticated way of computing things using particles. And I think the discovery of spin is kind of like stumbling across this like computational architecture. If it's not obvious, I'm a big proponent of the simulation hypothesis.
I can tell based on the way how the type of vernacular you're using. Actually, I wanted to actually come to another question that we didn't exactly go over. Does every particle have spin, or is it like only electrons? Like, does protons have spin, neutrons, all these particles?
All those particles. Every particle that makes up physical matter spins at the same rate as the electron. There's kind of a weird rule that if the particle is rotating at a rate of 1/2 of Planck's constant, then two of them cannot occupy the same space. And so all of the particles that we know that make up matter, like electrons, protons, all that stuff, they spin at 1/2 Planck's constant rate.
Gotcha.
If they spin at like not a fraction, if they spin at a rate of an integer multiple of Planck's constant, then you can pile them all up in the same space. You know, you can have 1 million photons occupying the same physical space. There's only one particle that we've ever discovered that has no spin at all, and that's the Higgs boson, but who knows if that's really even a particle.
I see. Yeah, so actually this there's an audience question that ties to this, which is, could you say something about spin 0 particles? What about spin 2 particles versus the way electrons spin?
That's a whole can of worms. Spin 0 and spin 2 are very, very special. There's only one particle that we know of that has spin 2, and that's the graviton. And you can actually show in string theory that if a particle does have spin 2, then it has to give you gravity.
Okay.
Yeah. Unfortunately, my string theory is a little rusty, so I don't exactly remember how the argument goes. But yeah, I know it's like very generic that like, in string theory, spin 2 has to be gravity. spin zero sucks.
That is a
spin,
interesting judgment.
how do I how do I talk about spin zero? Spin zero particles really shouldn't be allowed to exist. But somehow we found one, and it makes no sense, and everyone's confused about how this kind of thing can exist.
What? Wait, you just said spin doesn't make any sense, and now you're telling me something without spin doesn't make sense.
Well, no, when you first discover spin, it doesn't make any sense, and then you realize, oh, this is like the binary code on which the universe is built. So now once you accept that, then you think, okay, everything has to have some spin. And then you discover something that doesn't have any spin. You're like, what the hell? Like, this is crazy.
Yeah, that I mean, it's the only particle out of everything we've discovered that doesn't have spin, correct?
Yeah, and that leads to huge theoretical problems too, because when we first discovered spin, it's confusing. But then once you incorporate it into the theory, you realize that it's actually crucial for kind of keeping the theory stable. Like particles that don't have spin, I don't want to use like technical jargon, but like spin can be used to like protect the stability of a theory. Gosh, does that even make sense?
I mean, we can just roll with it unless somebody asks a question about it.
Okay. Yeah, like when you actually for example, calculate the amount of energy in an electron, the fact that it spins is very important for keeping that energy less than infinity.
Okay.
Yeah, I guess one really rough way to think about it is that if you talk about this binary system as like plus and minus.
Yep.
When you calculate the energy of an electron, you get these cancellations between the plus and the minus, and that kind of allows the electron to make sense. If there's no kind of what's the word, yin yang type thing going on, then it doesn't really make sense in the framework of a theory. To have a particle that has like a yin and no yang, it doesn't have any kind of opposite.
Yeah.
It's very, very unstable. And so if you look at the theory of the Higgs, it's very, very unstable. And it kind of begs an explanation, but we haven't found one yet.
I see. That is interesting. I guess can we touch on a little bit of chemistry? Like, how does spin actually relate to chemistry as we know it? Like atoms and stuff like that.
Gosh, I don't know much about chemistry, but I would say insofar as I'd say it's very important insofar as that property I mentioned where these particles that spin at a rate of half Planck's constant, the fact that they can't occupy the same space, that's important for the stability of matter. Otherwise, things could just collapse. Everything could just collapse into the same space.
Yeah, like all the electrons would basically be where the protons are, essentially, right?
They could, yeah. I mean, that's not technically what keeps the atom stable, but there's other mechanisms for that. But you could imagine a scenario where what you're describing happens. Yeah.
Oh, I see. Actually, I revised my statement. Yeah, you're right. Okay, what I meant to say is all the electrons orbiting the same orbital in in atom speak.
Oh yeah. That definitely, yeah. The orbital structure of atoms would be completely different if electrons were allowed to pile up on top of each other. You wouldn't have the reason why orbitals exist is because there's a space issue, and you can't fit too many electrons in one space.
Yeah. Okay. There's another audience question that's asking, how does the spin of the neutron differ from the spin of the proton?
No, it's exactly the same. That's the thing. It's even the same as the spin of the electron. There's no difference. It's a weird. It's like the universe invents this binary code, and it's spin of the proton, spin of the neutron, spin of the electron, spin of the tau, spin of every single particle that we know that makes matter to any degree, even quarks, spin at exactly the same rate.
So you're telling me all for the most part, almost all particles that make up matter spin at half Planck's constant, effectively. Not effectively, but exactly.
Yeah, so every single particle that makes up matter spins at half Planck's constant, and every single particle that communicates a force spins at a rate of Planck's constant.
I see. I mean, so actually, one question is like, for the example of like photons, for instance, do they have spin, or how would you describe the spin of photons?
Yeah, so photons are an example of like a particle that communicates a force. And the theory says that particles that spin at a rate of Planck's constant will act as a communicator of force. So photons are in that category, yeah.
I see. And then another audience question is, does neutrino have spin?
Yep, same, 1/2.
Oh man.
Yep. There's only like, aside from graviton and Higgs, it's either 1/2 or 1 times Planck's constant. And if it's not a force-mediating particle, then it's a half.
Wait, small technical detail. Just slightly off track, but the WZ boson, the weak force, have 0, right? As well?
No, there's spin 1 because they're force carriers.
But because they have mass, they're allowed 3 states, like H,
Planck's
constant, 0, and negative Planck's constant.
They have 3 polarization states, but they're still wait.
And we don't have to belabor the point. I just wanted to, point out the
the fact that they have mass means that they can be crap. How does this work?
It's fine. all good. We don't have to belabor the point unless somebody asks us in the question. But yeah, for the most part, for most cases, you're saying force carriers plus minus Planck's constant of angular momentum spin. If it's a matter, then it's just half Planck's constant. Are there any matter particles that are like 3/2 Planck's constant? I remember
that's a really weird one. Like people like Nima likes to make the argument that like supersymmetry. There are certain theories, unproven theories, that do predict the existence of 3/2 particles. I mean, it's weird, right? Like, how can you have 0, 1/2, 1, and 2? Like, why wouldn't there be 3/2? I kind of see his point. It's kind of weird, but we haven't discovered any kind of particle that has 3/2 spin. But you think that like if the possibility exists, then nature probably takes advantage of it at some point.
Yeah, I mean, so we're talking about fundamental particles. Could you like do composite particles? Like, no, actually, I don't even say composite particles. Like composite systems. Say you put like 5 electrons, or like 4, or like let's say 10 electrons together in this like state. Could it be like considered compositely a spin 5 system?
Yeah, totally. Yeah, okay. Totally.
Yeah. The reason I say spin 5 is because it's Planck's constant divided by 2. And so if you have 10, it's 10 divided by 2, which is 5. So, okay, we have a few more audience questions. I'm guessing this is information. Could information be technically transmitted by spin using the conservation rule from one part of the universe to another?
Using the conservation rule of one part of the universe? Yeah.
I think conservation of spin, like conservation of angular momentum.
Sorry, can you repeat the whole question?
So could information be technically transmitted by spin using conservation rule from one part of the universe to another?
I would hesitate to use the word like transmission of information. So the classic example is that like if you have like a particle that decays, let's say like you mentioned before, let's say I have a composite particle and one of them is spin up and one of them is spin down. So we know that the whole thing has spin 0. It's canceling each other out. When that particle splits into 2 particles, we know that one of them will be up and one of them will be down. And some people like to say that if you measure one to be up, that communicates information to the other particle that it needs to be down, but that's actually incorrect. There's no transmission of information there. You could, there's a number of reasons why you can't consider that transmission. It's kind of predestined almost. So the conservation of spin does allow you to know things about very, very distant objects that you wouldn't have, that are too far to communicate at the speed of light. But that's you gaining knowledge about that object. It's not technically a transmission of information to you, if that makes sense.
Oh, I see. So like what if we were like on two opposite ends of the universe, and I have my particle that's entangled with yours, and let's say when my particle's up, yours is down. When yours is up, mine is down. And let's say I want to like send you some Morse code. So I keep like, flipping my particle up and down. Is that not transmitting information, or is that
no?
Different?
Yeah, it can't be, because if we're on two opposite ends of the universe, it's actually ambiguous whether or not you measured it first or whether or not I measured it first.
Okay.
In relativity, we'd be what's called space-like separated, which means we're not even causally connected, which means that the order of events between what you do and what I do are arbitrary. It can be flipped. So there's no way you can consider that transmission, because I could move to a frame in which I measured the spin of the particle first, and then I could move to a different reference frame where you measured the particle first, and then who's communicating to who,
Oh, interesting. So, but if we were time-like separated, meaning like we were at a like, I guess, causally connected, for lack of better words, then there would be a
That's
order.
The perfect word.
What'd you say?
That's the perfect word.
Causally connect. Okay, then we could say an ordering. Is that fair to say? No matter which reference you're in.
Yeah, you can only define a specific ordering of events only exists between causally connected points in space-time. So this idea that you can send signals using quantum mechanics faster than the speed of light is totally wrong.
Gotcha. That makes sense. We have another audience question. It is, how does the spin of an electron relate to the magnetic moment of the electron?
I believe it's intimately connected. It's like essentially the same thing. No, shoot.
I mean,
wait, no. The magnetic moment is about like the structure of the electron, like whether or not it has any kind of internal structure, I think.
I thought there has to be like some kind of analog of movement in order for you to generate a magnetic field, because there aren't magnetic charges, right?
Yeah, no, that's what I mean. If there's some internal structure in the electron, then there could be some internal movement, and that would generate a magnetic moment.
But if you have an electron that's just like, just standing still, for lack of better words, and it still has this intrinsic angular momentum of spinning, and so wouldn't that generate a magnetic field in some sense?
Is that true? I feel like the answer is no, but I know it kind of makes sense, but I feel like the answer is no.
Oh, okay. Well, I guess we'll have to look that up.
Yeah. No, because there's no physical extent. Because like if the electron actually were like a spinning metal object, then that would be correct. But the fact that it is essentially point-like means that there's nothing actually moving or spinning in there. So it's not, like we'd like to imagine it like a loop that's kind of spinning around, and that would generate a magnetic field. But I guess that's like even more. That's like another piece of evidence for the fact that this thing is not actually spinning.
I see. Well, to the audience member that asked us this question, if you join our Discord channel, we can absolutely answer it there, because we're not sure how to get in contact with you otherwise. But yeah, happy to answer it there.
Tim would be way better at answering that than me.
Yeah, I think he would know. So we're almost at time, and so I wanted to give you a chance to leave the audience with any parting words or life lessons that you've learned from spin. Yeah,
no, I think the discovery of spin is awesome. Like, I don't know, to me, it's like, wow, like the universe has a digital encoding language baked into it, and it forms the undercurrents to all of existence. And so, how can you not believe that we are, in a sense, living in some giant quantum computer?
That is one valid interpretation of what's going on. As you can tell, I may not be as convinced, but the evidence.
I'll convince you. You'll come around.
I mean, I like it. It's very compelling. It's very enticing as a theory, but I may have to side with Tim on this one at the moment.
Yeah, you'll all turn eventually.
Yeah, I don't know if it's just like because that's the only way we can really describe it effectively, or if it's actually that way, kind of like the mathematical universe hypothesis. But that's a story for another day. So yeah. So, but on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yep. See ya.
See ya.
Thanks.
Thanks.